Welcome back to another video in the ICNE1 video series. In this video, we'll be going through the TCP and UDP protocols and seeing how they work. So let's start off with TCP first. TCP is a connection-oriented protocol which allows devices to send data in a reliable manner. So what that means is that when two devices want to send data via TCP, they have to first establish a TCP connection with one another. This TCP connection is identified by using a socket. So all a socket consists of source and destination IP address, source and destination port number, and the protocol used. In essence, these are a socket can be viewed as the characteristics of the connection. And so each TCP connection will have different characteristics, making it a unique connection. And we'll see how that works in a minute. But with TCP, a connection is established between two devices. And TCP focuses on the accurate delivery of data. It doesn't really care about the speed. With TCP, it ensures that when PCA sends data to PCB, PCB sends some sort of acknowledgement back so that PCA knows that data really got there. And also, PCA will resend any data which is dropped. With TCP, a steady stream of bytes is fed to it from the application. It's up to TCP to then put those bytes into segments, so chunks of bytes. So in case it might be fed 1,000 bytes, instead of sending those bytes individually, it packages those bytes into a segment, into a chunk, and then if it sends that segment down to the network layer, so we can add on the IP header. This is called encapsulation. So with a socket connection, let's say we have one server over here, and this server could have many different TCP connections connecting to it. Let's say this is a web server, and it has many different TCP connections connecting to it. How does this server differentiate between the different TCP connections? It uses the socket for that connection. So as I said before, each socket will consist of a source and destination IP address, source and destination port number, and protocol type. Each connection will have a different socket. It will. So no matter, even if these TCP connections all came from the same device, the source port number on that device will be different because the source port number will identify a different browser window. So by using a socket, it allows us to uniquely identify each TCP connection coming into the device, because each socket essentially defines the characteristics of that TCP connection. Each TCP connection will have different characteristics. So this is the packet format for a TCP segment. As you can see, it consists of source and destination port numbers, sequence and acknowledgement numbers, which we'll get to in a second. The checksum, the urgent point, and the window. The window is just used to define how many packets we can send at one time. Sequence number and acknowledgement number ensure accurate delivery of data. So let's talk about the features of TCP. Sorry for pausing the video, guys, but I thought just to clear up any confusion about TCP sockets, so I'll just go through it one more time. So with a TCP socket, it identifies the characteristics for that TCP connection. So in this case, we have PC1 and PC2, both with a TCP connection to the server over here. The socket for this connection would be source IP address 1.1.1.1, destination IP 3.3.3.3, source port of 1000, destination port of 80, and protocol type of TCP. The socket for this connection would be source IP 4.4.4.4, destination IP 3.3.3.3, source port 2000, destination port 80, and protocol type TCP. So as you can see, by using a socket, we can uniquely identify each TCP connection. So the PC knows, the server knows that this TCP connection is different from this one. So now when it receives data from its switch, when it receives data, it knows to what TCP connection this data belongs to, because it stores in its memory the TCP socket for each connection. So it knows that that when it receives a packet and this packet has this information in it, then this packet belongs to this TCP connection. So it knows that when you see the packet has the IP address 1.1.1.1 and the source port 1000. It knows that this packet belongs to this TCP connection. When you see the packet with an IP of 4.4.4.4 and a source port of 2000, it knows that packet belongs to this TCP connection. So it can differentiate between the two devices and can differentiate between the two different TCP connections. So let's now finally move on to the features of TCP. Okay, so TCP divides up the streams of bytes it receives into TCP segments. So the way it works, our application actually feeds bytes to the transport layer. And then it's up to TCP to then package those bytes into what's called segments and send that down to the IP layer so we can add more information on the packet so it can be successfully sent. So you could think of the application just feeds the individual bytes. Then it's up to TCP to format that data in a way that the network layer can understand, and so a way that the network layer can then route that packet and add information to that packet. So in essence, what TCP is actually doing, TCP is actually preparing that data so that for the lower layers of the OSI model. So it receives a stream of bytes, put those into what's called a segment, and sends that segment down to the network layer so that IP can now encapsulate that traffic in a header so we can tell that data where it's going end to end. A TCP connection is established by using synchronization and acknowledgement messages. The way it works is, let's say we have two devices connected together over many networks. Device A wants to initiate a connection with device B. Device A sends a SYN message. This tells device B that, look, I want to initiate a TCP connection with you. Now that SYN message is assigned a sequence number which is chosen at random during the synchronization process. So imagine that this SYN message has the sequence number of 1. When PCB receives this, it's going to send a SYN message of its own telling PCA that he too wants to establish a connection with PCA, but also an ACK message acknowledging that it's received the SYN message originally sent by PCA. To do this, the ACK message will actually list a sequence number 1 higher than the sequence number of the SYN message. So essentially, when PCA receives this, he says, oh, okay, PCB wants to establish a TCP connection with me as well. But he's also received the original SYN message I sent, because he's sending back a acknowledgement message with a sequence number that is 1 higher than the sequence number of the SYN message I sent. And the only way that he would know that sequence number that he sent to me is 1 higher than my original sequence number in my SYN message is if he received my SYN message. PCA will send a acknowledgement message back acknowledging receipt of PCB's SYN message, and imagine that PCB SYN message had a sequence number of 1000. PCA would send back a SYN message with a sequence number of 1001 acknowledging receipt. Again, these sequence numbers are chosen at random. So because they're chosen at random, the only way that PCB would know that sequence number 2 is 1 higher than the original sequence number of the SYN message that PCA sent is if it received that SYN message. So but these devices do not agree on what sequence numbers they're going to use. They just choose any random one. And so the acknowledgement message acknowledges successor receipt. So now the TCP connection has been established. It's a secure connection. So, like I said before, with TCP, each byte of data is given an individual sequence number. And the reason why we give each byte a sequence number is so that when the data arrives at the destination, the destination application can then reassemble the data in the order it was sent. So the way it works, data that was that was sent first by the application to the browser is given a lower sequence number than data that was than bytes that were sent to TCP at a later time. A bit confusing actually. So the way it works, okay, so we know that the application itself feeds bytes of data to TCP. bytes that of date. So the bytes that have a lower sequence number are bytes that were fed through first by the application to TCP. Bytes with a higher sequence number are bytes that were fed through afterwards. Essentially, by giving each byte a sequence number, our destination device can reassemble the data in the order that it was fed to TCP from the application. So the stream of bytes are actually fed to TCP. The destination device can reassemble that data in the same order that data was originally sent to TCP. And by using sequence numbers, we can acknowledge receipt of a whole block of data with just one sequence number. And so the way it works is that imagine that these two devices are sending data, and so we package these bytes into this packet, and the last byte of data in this packet has a sequence number of 1500. When PCB goes to respond and send an acknowledgement back, it sends back an acknowledgement with a sequence number of 1501. That means that not only did PCB receive the byte of data with sequence number of 1500, it also receives all bytes with a sequence number below 1500. So all bytes of data with a sequence number up to 1500. That's how we can acknowledge a whole bunch of data, a whole bunch of bytes in one go by using one acknowledgement message. And TCP supports flow control and ensures the destination device doesn't get overloaded with too much traffic. The TCP supports what's called a sliding window. So when the TCP connection is originally established, the sending device will only send one packet to the destination device. Once that packet has been acknowledged, it will start sending 2 packets. Once they have been acknowledged, 4 packets, then 8 packets, then 64 packets. So the way it works is that the more packets we acknowledge, the more packets that the source device can send to the destination device at one time. This is known as the TCP sliding window. We increase the window size to allow the source device to send more data at once to the destination device. Now with flow control, if the destination device starts to get overloaded with too much traffic, and so what happens is that when it's overloaded, some traffic is dropped. PCB can actually tell PCA, look, I'm getting overloaded with too much traffic. Can you stop sending so much data to me at once? PCA can pull back the sliding window, make it smaller, so that it now sends less data packets at once to PCB, which allows PCB to recover and to be able to handle the amount of traffic that it's receiving. So the way it works with flow control, if the destination device is being overloaded with too much data, we can pull back and essentially reduce the amount of data we're sending to that device at one time. So the way it works is that when it starts to be able to handle that data, we start sending more. We keep sending more and more data until the destination device says, look, I'm receiving too much data, can you scale back? And then we start sending less data at once. So the TCP window is always sliding. So we're always sending more data. When the when the device gets overloaded, then we start sending less data so the device can handle it. And a connection is terminated using a FIN, FINAC, and ACK process. So the FIN message says, I want to terminate the connection. PCB will send back a FINAC saying, I want to terminate the connection, and I've received your message to terminate the connection. And then PCA says that I received your message to terminate the connection, and then the connection is brought down. FIN, ACK, FINAC is the same process as well. So well-known TCP port number. So before we go on, TCP is normally used for web browsing applications and for email applications. It is focused more on accurate and reliable delivery of data and less on speed. Well-known TCP port numbers: 21 for FTP, 23 for Telnet, 25 was SMTP, 53 for DNS, 80 for HTTP, 110 for POP3, and 143 for IMAP. So now let's move on to understanding what the UDP protocol is. Okay, so UDP is a connectionless protocol, which means that when devices when they send data using UDP, no connection is set up between those devices. So there's no way for UDP to know. So when using UDP, there's no way that PCA would be able to make sure that data is sent successfully arrived at PCB, and there's no way for PCB to tell PCA to resend any data which is dropped. So why do we use UDP? With UDP, because it has much less features than TCP, the UDP header it contains a lot less information, which makes it smaller, which means that data can be transferred between two devices much quicker than with TCP. Remember, with TCP, it takes time to set up the connection. It takes time to resend any lost data. It takes time to acknowledge receipt of data. That all takes time. With UDP, it's different. With UDP, we have no flow control mechanisms. We have no resending of data, no acknowledgement. It's simply we send the data and hope that it gets there. And so it makes the data transfer very, very fast. And for applications like voice and video, which the most important thing is the speed of data transfer is vital, those applications use UDP. Because as an example, when we're video streaming or when we have a voice phone call, we want to make sure that the data we're sending between the source and destination device gets to the destination as quick as possible in order to keep the voice phone call or the video stream smooth. If some packets drop, then we'll see a little blip or some buffering, but it's not going to really affect the voice phone call as long as most of our packets get there. Now, if we try to use TCP, the packets would be sent more slowly, which would mean that our video stream would be of poor quality, it'd be buffering all the time, or our voice phone call would be breaking up. So the speed of sending data is vital when it comes to certain applications, and those applications use UDP instead. So as you can see, this is the format of a UDP header. And as you can see, it's much smaller than a TCP header. All we have really is source and destination port, and the checksum and the length. The features of UDP. So UDP just keeps sending packets to the destination device and doesn't resend any lost packets. So it just hopes that the packets get there. There's no way for the destination device to confirm receipt of the packets. There's no error recovery. And if we want to have reliability, then the application layer has to define how we do that. There's no windowing, no sequencing, no acknowledgement, and lower latency. So latency is the time it takes for a packet to travel from source to the destination and back. Because UDP packets are much smaller than TCP packets, UDP packets can travel to the destination faster, making them ideal for voice and video applications. And UDP uses the port numbers 53 for DNS, 67 and 68 for DHCP, 69 for TFTP, and 123 for NTP. So these are popular UDP port numbers. As you can see, UDP is used by a lot less applications. So with UDP, if we have these two devices over here, we're sending data packets. We have no way of acknowledging any receipt, but no way of receiving any data. Now, this doesn't really impact a voice or video phone call, because if we're video streaming, if a packet drops and then 10 seconds later we try to resend that packet, that's going to make no difference to the movie. Any packets. So what I'm trying to get through to you guys is that UDP is used for real-time communications. If a packet drops 5 seconds ago, we don't want that same packet to be resent 5 seconds later, because we're communicating in real time. It's not gonna, in fact, it actually cause more hindrance to the video stream or for the voice phone call if you did resend drop packets. So because it's real-time communication, any drop packets don't matter because those are in the past. We don't want to resend. We're focusing on the present, and so that's why UDP is vital for real-time applications. So we reached the end of this video, and I just want to kind of recap on what we've covered. TCP is slower than UDP, but allows for reliable data transfers, normally used for email and web browsing, and normally sends unicast traffic. UDP is faster, but doesn't guarantee that the data will get there. It just hopes it gets there. It's best effort. Normally used for VoIP and music streaming and video streaming, and supports unicast, multicast, and broadcast traffic. Unicast one-to-one, multicast one to a group, and the devices in that group are part of the same group as the sending device, and broadcast is one to all. I hope this has been informative for you, and I would like to thank you for viewing.